this was Mr. Phung's. So I got to put a little of my spice on it. Alright, so the X-ray tube. So we're going to be going over each and every one of these on here. But I'm going to give you a briefing. So basically this is the tube right here. So we have the cathode side and the anode side. So they do know this, right? They know the cathode and anode, right?
They should.
Okay. So on the cathode side, is it positive or negative?
Negative.
And then anode?
Positive.
Okay. I don't know what everything they know. So I was
So-
going to say
All right, so right now, looking at this picture, left side or right side, which one is the cathode side?
Left side is a
The left
cathode.
side.
Why do you think it's the left side?
There's
The
a
filament.
filament.
It's a sign over
There's
there.
a negative side.
And plus the filament. The filament is on the negative side too.
Okay, they do know a little bit.
All
So
right.
I'm making sure.
Great.
My
Okay,
finger's
and
still
on
up
the
there,
side
so-
it has positive. And then this is the glass envelope. Then you have your rotors and your stator. Is it on here?
Mhm.
Stator is this one for you?
Stator's inside one.
Okay.
Or outside one, I mean.
Oh, motor winding, okay, there
What
you
am
go.
I using?
And the lead housing. This is everything around the tube.
Blue is
And then
stated.
it shows on here you have your focusing cup and your filament. And you see how the electrons are going this way.
Orange is stated.
Okay, so first we're going to be talking about the protective housing. So as you can see, this is the tube right here, okay guys? And then around it is the housing. So the protective housing, it holds the X-ray tube. And it's lead lined. So this is it right here. So why do you think that we have it lead lined?
To prevent leaks.
Okay, it's right there. Okay, so X-rays are produced isotropically, meaning that they go in many different angles. Absorbs X-rays going in the wrong direction, like you said, leakage. So that's what the protective housing does, it catches the leakage. It must be limited to less than 100 milliroentgens per hour. And this right here, guys, you guys need to know this. Okay, so Mr. Phung, I did have a question on this one.
Yes.
So it's milli what? Let's see.
So this is millicoulombs.
Coulomb? Okay.
Mhm.
So you need to know 0.0258 millicoulombs per kilogram per hour. So this is important. We just reviewed over this.
I thought capital C was Celsius.
Degrees C is Celsius.
It's an electrical insulator. Do you guys know the difference between insulator and conductor? So what's an insulator?
See?
You guys know what a conductor is?
Dude,
Conductor?
I am so shocked.
No, not that conductor.
We're adults.
That's for the
Insulator
Why
probably
don't you
absorbs
say-
and conductor
What? Well, I'm
almost
not gonna just give it out for free.
So a conductor is basically something that can conduct electrical charge, and then an insulator is basically something that doesn't allow electrical charge. Yeah. So it uses high current and voltage. Thermal cushion, and so basically around the tube we have these insulating oils right here. Oil bath and cooling fans to keep the tube from overheating. It's very important that the tube does not overheat.
Right, so let me just make sure that we are clear on something. When we have our X-rays, right? Just imagine like the X-ray tube. Which way is the X-ray going when we shoot our X-rays? Which way are the X-rays going?
towards the IRs.
Right, that's right. We want them to go towards the IR. Right? So if we have got our tube like pointing downwards, which way are the X-rays going? Downwards. Great. So does that mean that when we create X-rays so that they go downwards? No. When we create X-rays, which way do those X-rays go?
Towards the patient, towards the anatomy.
So what does isotropically mean again?
Every direction.
Every direction. So I want you to think of the X-ray tube like a light bulb, right? You have a light bulb, you turn it on, which way does the light go? Every direction, right? If you have a flashlight, inside the flashlight there's a light bulb, correct? Which way does the light in that light bulb go?
Very fine.
It still goes every direction. But the flashlight only points the light one way, doesn't it? How does it do it? Because it blocks the light from going all the places it doesn't want light going, right? It's inside basically a cup, so that the light that goes the wrong direction is blocked or reflected to go the correct path. So keep in mind, when we produce X-rays, X-rays are going in all directions. We cannot aim X-rays during X-ray production. The only way we can aim our X-rays is by blocking every single X-ray going in the wrong direction. And we only let the X-rays going in the correct direction get through. Does that make sense?
That's why it's lead lining.
Correct. And so that brings us to lead lining, that brings us to leakage radiation. Right? Leakage is the radiation going in the wrong directions.
So basically in this picture right here, you see that it can go this way, it can go any way, right? So it's going up here, this is the leakage radiation that's capturing right here.
All right. Speaking of which, lead line protective housing, how heavy do you think that is? Heavy. Anyone think that they can pick up the protective housing?
This one?
Anyone want to
Yeah,
come
Jay,
over and
yeah,
try?
it's right there.
Because I've got one sitting right here.
Jay, go get up.
I mean,
You look like you picked it up pretty easily.
Jane.
Oi,
How's that?
fine for you.
like
He
26.
works out.
Oh,
Yeah, he
26 is
works out.
decent. That's a decent weight.
Oh.
It is heavy.
It is heavy, isn't it? Right, so this is our protective housing, right? Lead line makes it very heavy.
He dropped it for you. Be
And like I
careful
say,
with it.
guys, please make sure you write down this because this will be on your test. That amount.
What is
It must be limited to less than, what must be limited?
100?
The leakage radiation.
So we have a question over here.
What's 100
Milli
So
rings.
milliroentgen.
And what do Röntgens or coulombs per kilogram measure?
exposure?
Yeah.
Great, exposure in air, ionizations in the air. Very good.
As opposed to air karma, which is like disintegrations in the air. Or
As opposed to air karma, which is kinetic energy in the air.
Okay. So if the machine is being used for an extended amount of time, it can become very hot. So most stationary fluoroscopy units keep the tube housing under the tabletop. Mobile fluoroscopy units have the tube and housing easily accessible. Do not attempt to use the electrical cable as a handle, meaning these. Do not pull these up. So, actually, I didn't know this until Mr. Phung told me whenever we were first here, that you can actually go in and look at the tube and it'll tell you which side is the cathode and which side is the anode. So these are the cooling fans right there. So like if you look, like it's in the back right here, right? Well, for this one. And then the cooling fans right here, and then this is the X-ray tube housing. Okay, so now we're going to talk about the X-ray tube. So inside the tube is a vacuum. Why do you think that is?
And first of all, what is a vacuum? Are we talking about like zzz?
space without air.
Okay.
Resistance.
Okay, space without air. Okay.
Resistance.
Without resistance, okay. And so, all right, and then going back to Ms. Hawkins' question, why do we want the tube to be a vacuum? Why don't we want air inside the X-ray tube?
Aside from like the energy being inhibited, you would also have well, air isn't necessarily an insulator. It's more so it's just there, you know. So if you want to be able to control the entire process, you have to have it completely devoid of everything else.
All right, so let's go back to something you said earlier, something about inhibiting energy. Yes,
Is it
Angelica.
because electrons pass through air, like that. There's no resistance or anything to it.
All right, so I think the two of you are kind of on the right track. When we talked about producing X-rays, we said there were three things we needed. What were those three things we talked about? Great, source of electrons. Okay, acceleration, you need to move the electrons. And then stopping the electrons, great. So, let's say that I've got a source of electrons, and then over here I've got a place to stop the electrons, and I'm trying to shoot my electrons across, but I've got air here. What's going to happen?
Static.
Would the electrons have a straight path to my end
It kind of
target?
sucks it up and pulls it.
Well, there's the chance that the electrons could run into
Molecule.
air molecules, right? Molecules of air, right? So oxygen, carbon dioxide, nitrogen, whatever molecules you have in the air. Right? We don't want anything in the way of our electrons. We want it to be a completely straight path. So one reason we have a vacuum is to make sure that electrons go from cathode to anode without interference. But there is another reason as well.
Are you looking at me?
You want to take this one?
Isn't it like fire or something like that?
All
I don't
right.
know how to describe it, so you
Oxygen.
probably do it better than me.
Oxygen would interfere with the combustion. You want it?
Oxygen and combustion. All right, great. So, if you want to make a fire, right, what sort of things do you need? Air.
Oxygen.
Right, so you need oxygen and you need heat and something to burn, right? And if you want your fire to become bigger, you throw on more fuel, you add in more oxygen, right? If you want your fire to go away, what do?
So remove the oxygen.
Great, you remove the oxygen. So, in this tube, we said that we have a filament, correct? The filament goes through that thermionic emission. Right? The filament gets very, very hot. How do we keep the filament from instantly burning up?
We just said it, guy.
The fan.
If you don't want something to burn,
You take the
Oh,
oxygen.
Take the oxygen out.
you
That's why we
take
have a vacuum.
the oxygen out. Very good.
So that's how we're able to stop the X-ray from being produced.
So it's not about stopping the X-rays from being produced. It's about keeping the filament in a good condition. Right? Just like with your light bulbs. Well, not these light bulbs because they're fluorescent. But you know, like your old incandescent light bulbs, you get the little wire filament inside. You know, sometimes they would burn out after 4,000 hours, or so they say. Feels like they burned out a lot sooner than that.
Yeah.
Right? But how did they burn for so long? Once again, you take oxygen out so that there's no way for the filament to burn.
Okay.
I have a question for you. Sir, doesn't the electron need the cathode, the electron need a medium to travel?
No.
It, how does it travel then, the wavelengths? Waves, it's in a wave,
The
right,
electron
sir?
is a particle.
It's a particle. It doesn't need any medium to travel, sir?
It does not need a medium to travel.
Space is a vacuum as well. We have the sun though.
That's right. So just like traveling through space, you can travel through a vacuum, no problem.
Okay. So there's two parts. House in the glass envelope. We have the cathode in and we have the anode in. So in the cathode, we have the focusing cup, the filament, and then in the anode side, we have the target and the induction motor. Envelope is made out of borosilicate glass due to heat resistance. That's a star right there too.
We need to know the type of glass.
Yes.
You need to know the glass.
Cool.
That's a star right there.
Similar to like Windows being lead equivalent. all that.
Honestly, everything on Mr. Phung's PowerPoint is a star, honestly. Back to that. Okay, so let me talk about, sorry, I was in my mind. So let's look here. So we have the cathode in, which is negative, right? And then we have the anode in, which is positive, right? Right here is the anode disk. So X-rays travel, how do they travel again?
Isotropically.
Okay, but also
Everywhere.
electrons, how do they go from here to here? Or are they traveling from here to
Waves.
here, or are they traveling here from here? There you go. All right, and then they exit through the port. So they go from the cathode to the anode, and they live through the port right here, okay? And then these are the stators, and this is the rotor.
And what is the other name for port?
Window.
Window. So make sure you do know both those names.
You have to name the window
So for port, it's also called window.
to the wall.
And that is the part of the glass where the X-rays will be leaving the tube and going towards the patient.
Oh, that's gonna be stuck
And
in my
also,
head
sorry,
all
I didn't
day.
state it, but you guys need to know what it's made out of: tungsten and radium.
Do we need to know why tungsten and radium?
You do.
We're gonna get into that.
So radium being like the high temperatures and all that?
We'll get to that.
Okay.
So because X-ray leaves the
That's how you
tube.
remember, Jane.
You use some other words.
I know, yeah.
This is the
easy.
part, what is the
Hey,
point where the X-ray leaves
I'm already
the tube?
thinking.
Oh, okay.
Port is
I'm
like
already
an electron beam.
Say it again.
Electron beam.
For what?
Or the
Easy,
electron beam.
easy.
So,
So it goes from the cathode to the anode side. So right here is the focusing cup and the filament, right?
Okay,
So once it has thermionic
like
emission,
90s, early
it has
2000s.
kinetic energy that goes to the other side. So it's moving. So the electrons are moving from here, and once they hit the anode, they produce X-rays, right? And it goes down this way.
I'm sorry.
It was
Sorry.
something like that. It was called something.
What are you talking about?
Like in the rack tech, it was this was called something.
The
Like,
disc?
this was thermionic emission.
Thermionic emission is basically where the filament heats up, and then it produces like it keeps.
Electron beam.
so yes,
Electron beam, yes. So it goes from here to here,
that's
and then
right.
it goes down.
So the tungsten will stop it, right?
And then you're talking about the rotating
So
anode
that
disc
shield,
or
that
whatever?
thing in the middle, that's called the tungsten will stop the electron beam. before it
So
goes
electron
into-
beam will hit it, and once it hits right here, where he's pointing, right here.
And then how does
That's
it get to the anode? So if it hits and reflects
This
away.
is the anode.
This is the anode
Oh,
right
this
here.
is the anode.
hmm
I
So
see,
this is
sir.
part of the anode right here. So that's anode disc. You see?
The tungsten is the part of the anode. No.
Yes.
Tungsten is the part of the anode.
Hmm?
That's what.
Right here.
oh,
This one right here. See up here?
I see. This is the. I didn't realize that before.
We're gonna go more in depth.
Yeah, we're gonna go in depth.
We're gonna go very in depth.
Oh my goodness, yes. Okay, so the cathode is the negative end of the tube, provides the source of electrons needed for X-ray production, made up of filaments and focusing cup. Like I said, so right here, see, look, and guys, don't let the pictures throw you off. If you see this right here, this is the cathode sign because it has the focusing cup, right? See, if we went back on the other side, the cathode is on this side, right? So I just want to let you guys know that even though the pictures are flipping, you just need to learn where each part is, okay? So the focusing cup's right here, and this is the filament right here. And so the electrons are getting shot across to the anode side, which will hit the target, and then we'll be exiting through the port, which is not on there. But port should be right here.
Target.
So the target, so I'm
window.
gonna get into more into it, but this is basically is where the target is. It's targeting for it, basically.
Right.
Kind of think about it like that. So this is the glass envelope. We have our rotor right here, and then we have our stators. Did I miss anything? And then yeah, this is the target right here. I'm just waiting to see if you were gonna
I
add
read the
anything.
definition of rotor, but I forgot. But what is the rotor for?
We'll go into
We're
it.
gonna go into it.
Are we need to know the
Oh, no problem.
coils and electromagnetic, like the currents and shit that go with the. Sorry. Okay.
It's okay.
Okay.
So, what is the question?
Are we gonna need to know the exact energy of which the anode helps stop the electron beam? So like the rotor, stator, all those relationships. Okay.
Yes, you will.
Okay, so this part, the filament is part of the cathode, so we're gonna get into that. So there are usually two filaments. which is also called the dual focus. Filaments are 7 to 15 millimeters long and 1 to 2 millimeters wide, made of tungsten with an additional 1 to 2% thorium. Guys, this is very important. Make sure you write this down and take a picture and try to memorize this for sure, because you have to know the numbers too. It's very important. So tungsten, why do you think we use tungsten?
You have middle point.
High melting point, yeah.
we turn off the lights? It's kind of hard to see.
Thank you. I'm struggling back here.
You want to come sit up here?
No. Being off is perfect. And good thing I have Veronica. She will say, you can't see that, can you?
So yes, we have tungsten because it has a high melting point, but the atomic number is 74, and the melting point is 3,400 Celsius.
So it's very heat
So-
resistant.
And basically, you need to know both of those. That is
This
important.
probably didn't hit your eye. It was right here for a minute.
It's a lot of remembering numbers
Oh,
on this chapter for sure, and percentages. Yes.
Do we have to know the atomic?
Yes. You should know.
Yes, you should.
For tungsten?
For tungsten,
Okay.
atomic number 74. Just out of curiosity, does anyone happen to know the atomic symbol for tungsten?
G.
Not TU,
Z.
not Z,
G.
not G.
PG, sir.
No, we've got like 24 other letters that we can go through.
PG, sir, last time.
You.
Not U.
Use uranium.
U's closer though.
It's
Why?
UG.
Not Y.
Tungsten,
So V, because you could.
Not V.
Z.
T.
U was halfway there.
Z.
Not T.
Z
not,
is in
not
no,
Z.
Z.
V.
Zebra.
Not
Maybe
V.
not.
T.
I think we have a table somewhere.
R.
Periodic table is you take a periodic table.
Once again, U is halfway there.
This
Oh,
is
Oh, W.
Oh.
Yes. Very good.
They had a singer in their head.
I was.
I know, look.
Yep, so yes. Atomic symbol for tungsten is W. Why? Because I believe its original name was something like wolfram. So, yeah, wolfram.
Only W, sir. Only W.
That's W. Yeah. Fancy name. So no, you don't need to know that. Just random fact, right? Random bit of trivia. But yes, know that it's atomic number 74, high atomic number. Right? Only the second atomic number you will need to know. Not necessarily right now. But the second one you do need to know is barium, which is 56. Okay, so barium is atomic number 56. Tungsten is atomic number 74. Okay. High melting point, 3,400 degrees Celsius.
What is that in Fahrenheit?
Let's see. So to convert from Celsius to Fahrenheit, we basically take that, divide by 5. So that's going to be 680. Multiply that by 9. So that's going to be
Definition.
6, 9, 54, 7, 6, 1.
So you're still going?
Human
Like 6120.
I'm trying to write what he's talking about.
And then add 32, so it's 6152
Don't worry
degrees
about it.
Fahrenheit.
Don't worry about what they come from.
So it's over 6,000 degrees Fahrenheit.
I'm glad we're with scientific.
Okay.
Don't be confused.
Yeah. Right. This is, it can withstand temperatures hotter than the surface of the sun. Okay. That's how heat resistant tungsten is.
And then thorium allows for more thermionic emission. So, like this guy, this is the dual focus. There's two. This is the focusing cup that's holding the filaments. And these are the wire filaments for a small focus spot, and this is for the large focus spot. So this is important too. Well, you just need to know, like, if you look at this on like a test and he points at it, and he's like, which one is the small, which one is the large. You can look at it like that.
And they're the
So which one is
same.
the large? Oh my bad.
No, you're good.
This one's the large.
Same
and
material.
This one is
I was-
small. They're same material, yes.
Okay, so the filaments are the same.
They're made. The filament's made of this.
So one of those is 7, one of those is 2.
Not necessarily exactly those lengths,
Well,
but
but like that relationship seems like
correct. That's same idea. One would be longer, one would be shorter.
would they both be the same weight?
Not necessarily.
Tungsten and thorium.
Oh,
And the anode is
And
also
Mr. Phung, I had a question.
Yes.
So when we were doing yesterday, you said that the reason why we have thorium is
Mhm.
also because it acts as an insulator, right?
No,
No,
so it was purely for thermionic emission.
thermionic.
So the idea is that thorium enables you to get more electrons out of your filament. Like more electrons can boil off, compared to just pure tungsten.
So
Yes.
both cathode and anode have tungsten.
More electrons.
Yes, so both cathode and anode will have tungsten.
But they're gonna have other parts of it too. That's not. So just remember these for this one.
Correct.
So does that
There's a
mean
lot you have to
tungsten
remember.
What do you
remains
need for
charged,
this one,
or
like for
positively?
tungsten?
For the
Cathode?
filament,
Like
for the filament, this is for the filament.
Filament has a tungsten and thorium.
Because,
Yeah.
so we are running a current through it.
So put that
So we
down
are
on
pushing
your
more
notes.
electrons into the wire.
Put filament,
From, okay.
and then put tungsten, thorium. But you still have to know these amounts. All of these numbers are very important. I see people writing.
That guy's a hater. The sword maker,
I like him.
he's a hater.
He always makes me laugh. I love Electron.
Oh god.
You just hate him, huh?
Wait till you see Michael Jackson. Mr. Phung,
Hey.
you know
I
what
know,
I'm
I know what you're talking about.
Aliyah,
Name
Yeah.
even starts with an
this
M.
is a picture of the cathode.
Yes.
And it has two types of filament. Two types of filament or both of them are present in
There,
It's quite
there's
amusing.
two filaments.
two filaments.
See the
with
two
dual-
filaments and there's dual focus. Remember that too. That's very important.
The two, one is a small filament and one is a big filament.
Yes. I forgot your name. Are you still writing? No, you can go. Okay, so now we're gonna be talking about the focusing cup. So the focusing cup is made of nickel, surrounds each filament with only an opening to the front facing the anode. Focuses electron beam at the anode through electrostatic repulsion. This is very important, star right there. Negatives repel, has a very strong negative charge, keeps the weaker negative charges of the electrons from repelling from each other. Okay, so right here, this is the focusing cup, and right here, as you can see, this is the filament. And then on this side is the anode, and right here would be the tungsten. Oh my gosh. And then right here would be the copper, right?
So that's spots where the electrons are like burning.
They're gonna be
and
going out. They're gonna be so right here. This is where the focusing cup is. This is the filament. This is where the electrons. They're gonna be staying right here until they get enough, and then they're gonna shoot across, and they're gonna hit right here. So this is like the target.
You can even see that part of this target has been kind of like
Yeah.
slightly burnt
Burned.
away
That's
right
what I was
there.
okay.
Right from the electrons hitting that location. So I do want to talk a little bit more about this focusing cup and this concept of electrostatic repulsion, right? Because if you think about it, we have this wire right here. And now we are using thermionic emission, we're using current and heat to cause electrons to come out of this wire, right? So now you've got all these electrons surrounding the wires. What charge do these electrons have? Negative. If you have two negative charges next to each other, what do they want to do?
They repel each other.
They repel.
They repel.
It's like when
So what is keeping all these electrons from just flying away from our filament because they are repelling each other?
The line in the shield, the lead shield things.
Here.
Or here.
The
glass.
focusing cup.
The focusing cup. The focusing cup surrounds the filament, and it's got an even bigger negative charge.
So
So-
it's basically focusing those electrons. So like think about it like that. So they're holding those electrons in.
Right? Because this electron now has to make a choice. Am I going to get repelled by this slightly negative electron, or am I going to get repelled by this super negative focusing cup? Well, it's going to get repelled by the focusing cup, and so it pushes the electrons together, even though they don't really want to be together. Does that make sense?
Yeah, that makes sense.
I also, whenever I was studying this, like I just remember like the focusing cup basically looks like a little bed. And this is just like the way I think. It looks like a little bed and it's holding in the electrons, like, you know, they're just like sitting in there cuddling and hanging out with each other.
Yeah.
So it's kind of like a bed. That's what it looks like to me when I look at it.
It's sort of limiting the
So
electrons
it's
to
not
go.
a filament, it's.
Correct.
It's
Limits
the
the
focusing cup
electrons.
that's keeping the electron there.
It's just in the building.
Surrounding the filament.
Yeah, so look, this is the filament right here
That's the filament inside of it.
on the inside. And you see this is the cup.
That makes sense.
And the electrons are between the filament and the.
They're being held in it, kind of like, think about like a, in there, like they're in like a, what is it called? A hammock. That's what I think
Yeah, I
of.
was
It's like
just
kind of
gonna
like a hammock. And like they're just holding all the electrons in there.
So basically, the electrons are just like buzzing around.
Yeah, they're like floating around. But they're not gonna go this way, that way. They're just staying right there until they shoot across.
So they're staying right there in the middle where the white line is.
They're staying like, they're just like floating all around here.
Mhm.
They're constricted.
What's image A again?
So image A,
Is that like
that is a
So-
very basic.
This is the anode right here. And then what is this side of?
That'll be cathode.
That's cathode?
Yeah,
so it's just a small
Well, can I
tube.
see the
Yeah,
It's
cathode?
short.
Can I see the cathode?
So this is the cathode right here.
The metal part?
And then this is the anode side.
Is the cathode the metal part or the whole of that thing?
So this
No,
is
Yes, this whole
this
thing.
whole side on this side. So if I put a line down the middle, right? This is the
Yeah,
cathode,
that's what we're looking at.
and then this is the anode. So same thing on this. Anode, you see how they match right here? Anode, and this is cathode.
It said the anode was made of copper and
So
Tungsten.
we'll get into that when we
Then
talk
it's gonna-
about
Yeah.
stationary versus rotating.
physical.
He's like, let's jump ahead over the
I like it. I like it.
You read your book.
Guys, good?
What's up? Yeah.
Okay, so now we're gonna talk about the anode. So this is the positive end of the tube. Target for interaction with electrons to produce X-rays. Produces a lot of heat, and there's two primary designs, the stationary and rotating. See, look, we're getting there. Alright, so, like we said, this is the glass envelope, right? What side is this?
The cathode.
Yes.
The cathode.
Well, how do you know?
Well, because I look for the target, so I know that target is anode.
Okay,
The
so
opposite is
you're looking for
cathode.
this.
Yeah.
Oh, okay, and then what is this?
Cathode.
That's the filament.
Filament cup or?
Focusing
It's the
cup.
focusing
Focusing cup. Okay. Just making sure.
So it's the focusing cup and not the filament.
So the filament would be like on the inside right here.
So of the cup.
Yeah.
Bless you.
Let's see.
Sorry, thank you. I don't apologize for sneezing, bro. You human.
Don't ever do it again.
I'm not allowed.
Oh, can you go back, please? Thank you.
It's like
Sorry.
a Vienna sausage.
It does look like
You didn't see it?
The next one?
Yeah, the next one's the color. That's how I know Mr. Phung Hood.
I hope y'all understand me, because I'm over here trying to teach. I just ate pizza. I'm getting sleepy.
That's why I'm always up here walking around.
And I'm like, I should have. That's the secret. Walk over here.
Yep, that's the secret.
You gotta walk to the back now. You gotta do something different. Walk.
He's
The
always
phone
walking around.
phone just gonna go boop.
To walk this way as well.
So keep our eyes,
You know, it's like I'm
you
tired.
know, just
I go
like when
straight
you're
up on
driving,
flags.
you know how they say sometimes you gotta look around when you sleep. Let the window down.
He'll sit and then he wants to take off the mask.
Who doesn't want to take off the mask? Who's the one that's be talking about you?
I don't know why he always has it.
Yeah.
Just take it off.
I'm telling you, I bet you he can't wait to get rid of those.
He probably thinks about that with us on Mission Farm.
No comment.
No comment.
How come you don't keep everything?
It's the phone.
Miss Phung, you gonna miss it.
You guys good? Or are you still writing?
Yeah, we're good.
Okay.
Ooh.
Alright, so first
Tell
we're
me
gonna be
I'm wrong.
talking about the stationary
Tell me
anode.
I'm wrong.
A tungsten button placed on the slanted end of the copper rod Copper is a good electrical conductor. See, conductors and insulators are throughout this, okay? So what's a conductor again?
It conducts electric, it moves, that's,
Electricity? Okay.
Okay.
Yeah, so a little basic, but
Allows
it's good.
electricity to pass through.
That's all you gotta learn.
Okay, so what they're talking about right here, so this right here is the tungsten, and then around it is the copper. It is it's stationary because the target does not move. So examples of this would be like when you go to get a dentist x-ray, right? Ooh, look at me. Okay.
That's it.
So that's like an older design, only good for low exposure techniques, like when you go to the dentist.
Oh,
Like
yeah,
a panel?
those new ones that
So like think about when you go to the dentist office and they make, you know, you get x-rays of your teeth, right? So they would typically use probably a stationary
What about a panel? What would that be considered?
panel.
Like
yeah, the
Panorax?
one that rotates
Yeah.
around,
Yeah.
that's what she's talking about. Yeah.
Oh, okay, so that's
Panoramic,
more.
They have one
I still think that would
Panoramics-
maybe still be
Yeah, I think that might be a stationary one.
stationary, yeah, because it's still dealing with the teeth. So it's dealing with low exposure techniques, right? So in X-rays, we'd probably be dealing with the rotating.
Mhm.
So electrons only hit a single location. Target heats up too quickly for extended exposures. So that's the reason why dentists would use a stationary and X-rays would not, because it's the heat that we're worried about with this. May otherwise lead to tube damage, so we don't want to damage our X-ray tube, right? So that's why we would be using the rotating one, which is on the, I think maybe the next slide. But mostly you'll see these for dental offices and the one you said, Panorax. I think so, right?
Yeah, I'm not sure about Panorax. I'm wondering
I
if
feel like it would still be, because we don't really use it. Like if you think about it, we really
but it is a long exposure though, right?
It is
It
long.
exposes for like 6
Because
seconds.
the person does shingle.
Well, they showed you for dental x-rays
Yeah, they
as
do
well.
that too. Yeah.
Oh, yeah, they
So-
do.
They do, yeah.
Oh.
I would think
That's a
it's
good
really
question.
Well, it's
I'll
because
look
we
into
don't
it.
also, yeah, and we also don't like have a lot of patience for that, you know.
That's true.
So that's why I would think maybe not, because you're not heating it up a lot throughout the day like the X-ray tube, you know.
Stationary is only good for low exposure.
So basically, when the X-rays, the electrons are shot cross, they're basically hitting one area of the anode, of the target. So they're only getting hit in one area. So like basically, if I point this laser here this whole entire time and I hold it there, and that's how much exposure it's getting, right? So that's gonna affect it, right? So you wouldn't want your tube to lead to damage because that's overheating it. You see what I'm saying? Because you're leaving it in one spot. I'm trying to give y'all some examples. I think I might eat, but you guys good or are you still writing? Oh, one more? See what your phone really looking into it too.
Yeah. So far, I've found that it operates at 86 kV and 10 mA with a 0.5 focal spot. You also get this out.
Okay, so now we're gonna talk about the rotating anode. It's made it's a molybdenum disc with a slanted edge coated with tungsten and attached to a copper shaft with molybdenum core. Sorry. Say that 3 times fast.
Molybdenum.
Say it 3 times fast.
Molybdenum, molybdenum.
Oh, you already That's not fair.
Molybdenum.
Anemone. That's what I feel like I was saying.
Say monopoly.
Monopoly, like I'm playing. Monopoly. Molybdenum has low thermal conductivity and is a light but strong alloy. Rhenium may also be added to increase heat capacity and durability. It is rotating because the target spins around during exposure. Modern and most common design, so like for our X-ray tubes and stuff like that. So the difference between the rotating and the stationary is when the electrons come across and they hit, this thing is spinning. It's literally going around. So you're not just hitting
In the same
one spot.
They'll be
So-
in different spots.
Mr. Phung, I wish we could. Okay, I'm gonna do the little trick you did.
All right.
with this. I think I remember. Wait, it was like this. Yeah. Need a pin or something. Here,
Or probably better to use a marker.
marker.
Yeah, it'll show up easier.
Okay, so I'm gonna have you do it. Cause I'm gonna spin it around. Okay, so act like you're just shooting your X-ray straight first. Yeah. Keep going, just hit it like that. Right, and you're just holding it like this, right? So you're just holding it there. Think about that heat. That's like overheating the anode, right? Okay, now take it off. So that's stationary. Now this one, let me get this paper. So now this one is spinning like this. Now I want you to shoot your thing right here. You see how it's not just hitting one spot? Sorry, I'm messing it up. Mr. Phung had it bigger. Epic fail. But look at this one. Here, I got it.
I think
Still
I
good,
tape.
though.
Enough tape. You gotta tape it down.
True. But it doesn't matter. It's still showing my point. Mr. Phung.
That's true.
So this one's the rotating. You see how the heat is all in different areas, right? And then the stationary is just right here. So that's why we use the rotating one in X-ray, because you want to make sure that your X-ray tube does not overheat.
Why do they have like? Why are these things all these weird names? Like, why is it called molybdenum?
What does that word mean?
Like, why?
That's the name
It's
of
the
the
material.
element.
That's an
Yes,
alloy?
The material that's made of.
That's the name of the element.
It's the.
It's like asking why it's called copper or gold or silver.
I'm sorry, I didn't know.
Yeah.
It's okay. It's okay. It's just a name, right?
Oh, I was like, where is it?
Just like I'm called Mr. Phung, right? I'm sorry I'm not named something easy like Mr. Smith.
That's a little too bland for.
Smithy.
Yeah.
But yes.
So is molybdenum
Like I said, like you
Uh-huh.
look at that
an
image
alloy?
that I showed you.
No, it's an actual element.
It's an actual. What's the sign?
It's heating up. So you don't want
MD.
that
MD,
to
I
overheat
believe.
here too.
Okay.
It's not gonna be looking good, right? So you want it to
Let's
spin
double check.
around, because when it
'Cause I know
spins around, you're
rhenium is
holding it right
RE.
here, but it's spinning around, so it's not just hitting in one area, so it's not gonna mess
Copper
it up.
CU. No. Yeah, CU.
So it increases
Tungsten.
heat capacity
Or
and durability. So
MO.
it lasts.
MO.
Mr. Phung, I don't care. I'm proud of myself. I remember your little example.
You're good. I'm glad you remembered that because I almost forgot I did that demonstration for you guys.
Do you know what that means?
What does that mean?
Can you tell me? It was just your birthday, that's what.
Yes, that's right. I'm growing old and senile already. 33,
No,
right?
you're not.
I'm sorry, that may have been
Yes, no, you're not.
That means if you forget to add her
still my
points, it's
golden
okay.
ages ahead of me.
If you forget to add my point on there, the good thing is that I'm from 2000, so I'll remember.
2000 and?
Oh.
John is with an ass.
I just wanted to trigger you.
Where is it? What age is it over here? I don't have an age, I just have 2000. Get out.
She's making comments like she's not 2000.
Like she doesn't eat Tide Pods?
Oh.
I don't.
Cinnamon challenge though?
They
Come on.
don't work. Whoever uses Tide
All right.
Pods, they
So,
don't work.
anyone who has read ahead, how fast does this disc spin?
Pretty fast. It was.
I'll give you a hint.
60.
It's a familiar number you've seen before.
Oh, yeah.
No,
It was on one of these slides.
74.
No.
56.
No.
So it's pretty big.
Oh,
How fast does the rotating anode spin?
100.
No.
3,400.
3,400.
Yes.
That's.
Yes.
What?
Good job.
3,400
Oh.
RPM. So yes, 3,400. Not only is that the melting point of tungsten, 3,400 degrees Celsius, but as you'll see in the next slide, the speed at which it rotates is also 3,400 RPM. So it's convenient. You get to remember one number for two different purposes.
That was nice.
You said 3,400 M.
RPM, rotations per minute.
Yeah, it's
It's
gonna
gonna be on the next slide.
Lowercase.
Next slide.
Okay.
Oh,
I
like,
Oh, part two.
Sorry.
Part two.
How you doing?
RPM, rotations
per minute.
or revolutions per minute. Same thing. Oh, oh, we're already at line focus spectrum still?
I think so.
Where's the RPM? Slide six.
Oh, yeah, where's the RPM?
Dang, rip the OGs.
Maybe Meryl shook it up. Hopefully.
Maybe we didn't send it.
Oh, there it is.
Okay, so moved away. Yeah, I posted whatever we
Is it
switched.
really back?
Yeah, this is one of those you gotta
No, that's fine.
you gotta get
It's
into
culture,
it.
so this is, it's gonna fit.
Okay, so you want me to take it down?
So that's good.
That's also not his actual head.
Okay, so
I may have just misremembered the order.
I don't remember, like I can't remember the each slide I made. So we're gonna be talking about the rotating anode again, the motor though. So the motor is an induction motor, very important. Electromagnetic induction. If you have two of these, you can produce or induce the third. Electricity, magnetic field, or motion. So, do you need to know these?
Yes.
You do.
Oh, I put my pencil down already. I was like, okay.
So, electricity plus a magnetic field will equal a motor. Electricity plus motion equals electromagnetic. And then magnetic field plus motion equals a generator. Do you need to know this? Yes, you do. Isn't this still Faraday?
Correct, Faraday's law of
So, are
induction.
they gonna learn that one? Because it wasn't on here.
Yeah, so I think we'll go into it more in detail in physics. I think that's where we really
Okay.
fit that with the transformers.
Oh, okay.
Excuse me, sir.
Yes.
Since we
you're
did
gonna get
since we did this, we're getting the PowerPoint, sir?
It's a lot.
And then I don't
No.
need to take the pictures.
Dance with
No,
pathology
I'll send you the
chapter.
PowerPoints when we finish the chapter.
We're still learning. We're still learning some new stuff. But
So,
summer we just reviewed.
oh yeah, summer you just
Yeah,
reviewed.
summer is just review, and it's like over the anatomy and positioning and evaluation of radiographs.
Right.
And then now we're going back into all of this with Mr. Phung.
And they're also learning about radiation protection. They're learning about advanced imaging equipment, which includes like fluoroscopy. So you won't learn how fluoroscopy or CM works until next fall. Okay, but you will learn how basic X-ray machines work. It is a lot.
It is a lot. Let me
That's
tell
why you have 2 years. So, let's talk a little bit more about this rotating anode. Okay. Because if you think about it, right, to have a rotating anode, we need a way to spin it, correct? And normally you would use some sort of motor to spin it. But in this case, we are using a specific kind of motor. We are using an induction motor. The induction motor, right, as Aliyah said, works off electromagnetic induction. So let's talk about electromagnetic induction. You have 3 ingredients: electricity, magnetism, and motion. As long as you have 2 of the 3, you can create that third one. So, for example, does anyone know how a power plant works?
A what?
A power plant. Jay.
Isn't it some sort of fuel in motion?
All right.
So, like water or whatever.
Okay, so let's say that we have a coal burning power plant, right? So you have coal, we throw it in the fire, it burns, it makes smoke, and how on earth do we get electricity out of this fire?
Steam.
Okay, so we run some pipes past the fire and we make steam. But how do we turn steam into electricity?
Yeah, rotors that like force something to move.
Cody?
Some type of motor, like some type of thing that the steam can push against
that will rotate. Great, so we've got a turbine. We've got basically a giant wheel that the steam pushes against and turns. But how does turning what's basically a really fancy wheel give us electricity?
The centrifugal force probably.
How does centrifugal force give us electricity? I've got centrifugal force like this. I'm not making electricity.
Oh my gosh,
We could have attached it.
So how do we get electricity? Because that really fancy wheel that's spinning, guess what that wheel is? It's a magnet. So we have a spinning magnet. What two ingredients do we have?
Motion and.
Motion and a magnetic field. So we've got a spinning magnet, we have motion and a magnetic field. And when we have those two, what do we produce? Electricity. And that is how you get power out of a power plant. You spin a fancy magnet and you induce electricity in the wires. Does that make sense?
No.
Produce it. Induce means produce.
Induce means produce. So that is how a power plant works. You have a fancy magnet, it spins, and when you have a moving magnetic field like that, it creates electricity. Okay? If we go the other way, something like an electric car, like a Tesla, how on earth does it drive?
By itself.
Not very well by itself. At least not right now. Okay, so
Electric stores are that.
like in a normal gasoline engine, right? You press the gas, you pump the gas in, it explodes, it pumps the pistons, it does the little spinny thing, and the wheels move. But in an electric car, you don't have any fancy pistons or gas or combustions, right? How does an electric car drive?
With electricity.
Well,
Magnetic field.
once again, you've got electricity, and you run that electricity around a magnet. And when you have electricity and a magnetic field, what do you create? You create motion. So that magnet begins to spin, and that spinning magnet is attached to the wheels. So now the wheels go. Right? Is anyone familiar with an electromagnet? For example, like at a scrapyard, you know how they've got those giant scrap magnets that lift things up? Right? But that's not just a super fancy giant bar magnet that you find on your kitchen, right? That is an electromagnet. MRI machines, those are electromagnets. How do they work? You've got electricity, right? And you spin it through a coil of wire. So now it's moving in this circular direction. You have electricity, you have motion, what do you create?
Magnetic field.
A magnetic field. You create a magnet through that spinning electricity. Right? So as long as you have two items, you can create the third one. Are we okay on this point?
Yes.
Okay. We'll talk to you later. Yes.
You had a question? Isn't it Tesla that we this measure, right? For
Yes. Funny enough.
that's funny. I
Mhm.
use it.
Okay. So in the case of our induction motor, what do you think we are going to use? What two ingredients are we going to use in our induction motor?
Magnetic field for sure.
Great. We're going to use electricity, and we're going to use a magnetic field.
Okay. So there's two parts in the motor. So we have the stator and the rotor. The stators are outside the glass envelope. Electromagnets arrange in pairs on opposite sides around the rotor. And the rotor is inside the glass envelope, which has an iron core inside the copper shaft. The stator and rotor do not touch each other. And why do you think that is?
Because one
is outside.
Yes.
Good. So one is outside, one is inside. But why do we need it to be like that? Why are the stators outside and why is the rotor inside?
The stators.
one gets hot.
Why can they not touch each other?
Why are they not touching each other? Look at the image. So this is the rotor right here, right? And these are the stators around. And what is it doing? It's
One's rotating.
They're spinning, right? So, what? Why do you think that they're not touching?
The magnetic field,
Yeah,
they
it
probably
keeps-
have the
I
same.
heard magnets.
the
Was that magnets?
Because electricity rotation is motion is there and then
Look at Mission Florida. Why are you sitting down?
Would they be
They're
going
going to
into
be
each other? Is that why they're not
What
touching?
it is.
'Cause
I
they-
heard one. She said magnets.
So would they be going into each other because of the magnet?
One is a
But they're
stationary.
not touching each
Because
other.
they're same,
repel each other?
they're the same sign, so they're repelling and then creating.
Keeps it in motion.
And they're creating motion.
Don't talk to me.
So they're repelling and creating, because one, they're both the same negative and negative.
Okay, so what I've got so far, what I'm gathering is that you guys are saying that they're repelling each other, which is creating this motion here, right?
That's right.
Is that wrong?
Okay, good, but why is that important? Why do we want them to not, why can they not touch each other?
Because if they touch each
Why
other,
must one be inside and one be outside?
because if they come together, then they'll stop. There won't be any motion.
It comes back to something we talked about
One is
earlier
a
in the slides.
stationary. Anode.
Think back to your earlier
Oh, is it
slides.
that two negative field?
It's not gonna hold them in place. It's not gonna hold them in place.
So where are these located?
One is on the inside, one is on the outside.
Inside and outside of what?
The anode.
More specific.
The focusing cup?
The
Rotate.
What does it say on that first bullet point under status?
Glass.
Two parts, the filter and the
Oh, the motor.
Okay, glass envelope. One is inside the glass envelope, one is outside the glass envelope. So why is it important that one is outside and one is inside, and that they don't cross the glass envelope to touch each other? What did we say was important about the glass envelope earlier?
It's hot.
It focuses the.
Yeah.
Electrons.
Okay, hot, electron focuses electrons, but I'm looking for something else.
What else? What else does the glass?
It's heat resistant.
The glass.
What else is in the glass envelope? Or what else is not in the glass envelope?
So what?
You got your focus club, you got your filament, you got your
No.
anode, you
You're
got
kinda,
your
y'all are thinking a little too much into it. Air, so, okay, no.
vacuum. The vacuum.
There you go.
Oh, for real? Oh.
Oh, so there's no oxygen in it because of the vacuum?
So in order to keep the vacuum in the glass envelope, we can't have any openings in it, correct? We can't have things trying to pass in and out of the glass envelope like that.
The vacuum.
So that is why stators on the outside, rotor on the inside, they can interact through the glass without ever needing to compromise that glass envelope. So it stays a vacuum. Does that make sense?
What's outside you said?
Vacuum with both of them on the inside or on the
Here, I can
side?
show you again.
How are you gonna run the
Change
wires into
slide,
it
guys, real
if
quick.
it's inside?
Hold on.
How do you,
She asked me a
right?
question. Real quick.
Okay. But think about it, if there's a motor inside the glass envelope, how do you power the motor?
So this is the glass envelope, right?
Well, you gotta run wires to the motor, right?
The glass envelope, right?
And so the wires need to go from outside
So
to inside.
this
And so
is
that
the
point
vacuum's in the
is
inside, right?
gonna be a place where the vacuum can
So
break.
The vacuum is vacuum shut, like there's no air in there. It's airtight
I
area.
understand how you can have other stuff in there and it'd be okay. You can- Sorry.
So wait, the vacuum, the vacuum, what the hell? See, this is making me go crazy. So the vacuum is inside the cathode? The vacuum is
So
in
the vacuum is basically, there's no air in there. So it's not like a vacuum like this, right? It's not like a vacuum. The vacuum is basically, there is nothing there. There's nothing, there's no air, there's nothing.
Oh, that's the Phung.
Whoa, sir. Simmer down. You see what I'm saying?
Yes.
Because you don't want, the vacuum is basically, yes, the vacuum is on the inside. There's nothing in there, so there's no air. There's nothing in there. There's no air. There's no air in there. Because you don't want air for this don't.
It's okay, right?
So the reason, what he's saying is basically, the reason why we have the stators on the outside is because if they were, we can't open up the glass envelope because we need it to be a vacuum, right? So vacuum means what? What is a vacuum?
Nothing,
There's
no
no air,
air
right?
inside.
Okay, so if we had an opening here, there would be no vacuum, right?
That's right.
Basically, right?
Right. So it's not like you can't run gears there. You can't have any sort of opening, right? You can't have like ball bearings, right? Because air would find a way to sneak through there.
So right here, on this one right here.
Hmm?
So that's
So
why
look,
you
look,
have
these
one
are
on the
the
inside and one on the
stators right here.
outside.
You see how it's not in the glass
Oh, okay, it's on the
envelope,
side.
right? Yes. You see how this is the glass envelope, right? This is the stator, this is the rotor.
Oh,
And it
now it
spins.
makes sense.
So they spin around it, right? So they couldn't be on the inside.
What did you ask, Ray?
Now which is the glass area?
Huh?
How is there no air?
The glass envelope is right here. Basically, this whole thing right here,
Well,
this
You know
outline.
what I mean? Like, you know, it looks like.
This is the protective housing around.
Where is the vacuum? What is it? Like, where
there's
is
nothing.
So there's nothing in this. Think about
How did they
space.
take the
it?
air
How did they do that?
It's like keeping top on the.
It's invisible.
Vacuum is it's not a thing.
it
Vacuum
can-
isn't a
it
thing.
can have
Is
air.
vacuum is it invisible?
It's not like a physical thing.
Like
Oh,
on
yeah, I
here?
thought you meant like it's not
Is
real.
it like invisible?
What? What's
The
it?
vacuum.
So the vacuum.
It's there, but it's not
So
there.
this right here is stating that it's a vacuum. This whole thing is a vacuum, right? But there's no air. There's nothingness. Basically, think about space. There's no air in space,
It's
right?
invisible.
It's like oxygen.
So a vacuum is just a lack of
There's
air.
lack of air.
So you can't see air, right? If we take away the air, you can't see that we've taken away the air, right? But the idea is that you have this enclosed space with no air inside. Now, how do we create a vacuum? That is a very interesting topic that is probably outside the scope of this course. If you want to discuss different ways we can create a vacuum, you can stay after class and we can talk about it. Because there are several ways we can go about doing it.
That's basically what I'm saying.
There are some really cool ways to do it.
And what vacuum is
So-
there's a lack of air.
Like a vacuum seal pack.
Right, like a vacuum seal pack.
Turns, rotates, right?
Mm-hmm.
Within, inside the envelope.
Mm-hmm.
And what are the stators doing?
So the stators is making it move, right? Because of the magnetic field.
Because of the magnetic field.
So think about what batteries do, right? What do they do when they have North Pole and South Pole? They attract because they're opposite. Now let's say North Pole and North Pole, right? They repel each other. So on this one, this one's the.
Would it be easier?
Okay,
to-
so I think for your class we actually had this demonstration.
Yeah,
So let's get
stand up.
7 people up here, please. If I could have 7 people come
I
up
forgot
here.
how this one went because I wasn't part of it.
I also forgot how it works, but we will go ahead and just sort of add it.
We had a paper.
Yes, we need some paper. We do need some paper.
It's outside, like how is it? So it's just, the stator.
Is the stator and the rotor?
Positive, they're both positive or they're both
Alright, I'm
negative?
gonna turn the lights back on, okay?
I don't think that matters, does it?
Is that?
Yeah, sometimes it's magnetic about it.
Honestly, I feel like
So
the C is colder.
Now
that he said
This
that.
takes the stuff.
They're probably so positive and hang around, they're never touching,
Mr.
right?
Phung is low key a vampire.
So then they're supposed to be positive.
Probably 'cause it's just
Because they're both at the end, so they're
Hey, why are you
both,
looking at me?
yeah, they're both at the end. They're looking.
Oh, look what I was looking at.
Oh, like that. 2 more pieces.
Same
They're
tri-
not, but no,
same concept.
They're not
Wrong,
just
wrong target.
positive, they're South Pole and North Pole.
1, 2, 3, 4, 5, 6,
funny.
7.
You see on
Hurry up, you guys. I'm gonna record you guys. I'm gonna record you guys.
Hey guys, listen. I got it right here. Y'all asked me if, so is there North Poles and South Poles, right? Like what's different? So right here, it literally says North Pole right here and South Pole right here. And look, on both sides, there's a north side and there's a north and a south side, right? And then they're opposite of each other, basically. So that's why it keeps on
And it
continuously.
keeps rotating.
There you go.
Okay, 1, 2, 3, 4. Yes, I need 1 more person up here.
It's the magnet.
I need 1 more person. I need 1 more person.
I mean, I'll leave it right there.
I can do it.
Alright.
Thanks.
Okay, so I need 1 person who is okay with spinning around and will promise me they will not faint and fall
No,
down.
you got too much stuff going on.
No.
No, you got too much stuff going on.
It's
okay?
7, 8, 9, 10,
want me to be the
11,
runner?
13.
I don't know what's going on. We're gonna see.
Oh, wait.
Alright, I guess you'll stand in the chair.
Yeah.
Alright,
Okay, so
and then I need
You were over there.
6 of you to stand in a circle around J.
Okay, we're standing around.
Alright, everyone else, make sure that you are paying attention here.
Okay, so I have the north, so you need the south.
So make sure that there's someone on the opposite side.
So like
So
this.
Sindhu is here, I need someone on that side.
North right here. So you're gonna be Cody.
Okay, so Cody, hold on to both the green north and south. Or sorry, Jay. Sorry, Jay, hold the both. Yep, hold the green north and south. Yep. Melanie, hold that black north. All right. Cody, Angelica. All right, and then I need one more right here. And okay.
So I'm going with her.
So no, Aaliyah, you're just gonna be.
Oh, I'm just watching.
You're just. Yep.
Oh, okay.
All right.
You're with Cody.
So right here, you stand right here, Shamika. So you should be opposite of Cody. Angelica, you're opposite of Shaheen.
Yes, ma'am.
Melanie, you're opposite of Sindhu. So, magnets, North Pole, South Pole. If they come close to each other, what happens? They attract, right? North Pole, if they come close, what happens? They repel. South, if they come close, what happens? They repel. So, right now, hold up your, what do we have right here?
South.
What do we have over there?
North.
So, in the middle, we've got our magnet here, right?
Yes.
So, which one should be attracted to the south end? All right, so bring the north over here on your left side. All right, and then which one should be attracted to the north end?
South.
So, are they properly lined up now?
Yes.
Great. Now, we turn on the power. When we turn on the power, what's going to happen is each one is going to pass it over to their, let's say, clockwise. So let's go this way. So Melanie passes this way, and Sindhu passes that way. And when that happens, what happens to our middle? Keep going. Keep going.
Oh.
And that is how you spin something without ever touching it.
Yes.
Does that make sense?
Yeah, now it makes sense.
Okay, yeah.
So this magnet in here is made up of north and south.
Correct. That iron bar has a north and south. So as the stators change their polarities, that bar begins to spin.
And the part that's inside, what is that called?
So we call it the rotor.